Hi everyone, and nice to see you here. It's nice and early for some land surface modelling. Before I start, I should just thank Martin de Cauw, who I stole a lot of these slides from, which was real handy. So I think Nina actually showed this exact same figure yesterday and asked you all to name the different parts of the climate system. You all thought of the oceans and atmosphere really quickly, but I think geology was the closest we got to the land, which was a really good answer. But today I'll show you why the land is also an important part of the climate system. So hopefully when Nina asks you next time, that'll be your first answer. So in the climate system, the land is the lower boundary layer to the lower boundary to the atmosphere that sits around it and interacts with the atmosphere. It also has an impact on the oceans through input of fresh water into the ocean basins. And it, of course, also captures a lot of processes that are important to us humans and ecosystems, for example, many parts of the water cycle. So just a very brief history of land modelling. So you'll see from this figure, which shows the history of how climate models have evolved, that land models have been part of these models since the very beginning. And in fact, some versions of this figure suggest they were even added into the models before the oceans. They started off as very simple box models with a few fluxes of energy and water going in and out, but they, for example, didn't include any kind of vegetation in them, which we know is pretty important on the land surface. So over time they've evolved. In about the 80s and the 90s, simple representations of vegetation were included, things like photosynthesis. And that's also been a big part of the land surface development ever since. So we now not just consider the inputs of and outputs of energy and water, but also how the carbon cycles through the system. And we are starting to add more and more vegetation processes and actually make the vegetation interactive so it can respond to things like climate conditions. So I told you I would tell you why the land is important, so I have a couple of slides on this. And the first reason is that it captures a lot of the greenhouse gases that we put into the atmosphere. In fact, that's about 25% of the greenhouse gas emissions that we emit. It's taken up by the land. Another 25% is taken up by the oceans. There is some uncertainty around this. So this figure is the global carbon budget, if you wish. So what we put into the atmosphere through fossil fuels and land use, and then the sinks where that carbon ends up. So this land sink is actually calculated as the residual of the other terms. We don't have a good estimation of it from its own sources. So there's some uncertainty where we don't actually really know where that carbon ends up. But overall, it's about 25% ends up in the land. And in terms of the future projections, as we know, there's a lot of uncertainty in what's going to happen to the global temperatures going forward. And quite a lot of that uncertainty comes from the land. So how much carbon is it going to be taking up going forward? Is it still going to be 25% or something else? So it really matters for the long-term predictions of climate. The land is also important at the short scales, so sub-seasonal to seasonal predictions, so from a couple of weeks to a couple of months. So this figure here shows the different sources of predictability, so where the skill might come from in our forecasts. So you'll see at the very short scales of some hours to days, the atmosphere plays a major role in the predictability of the climate system. But at the scales of a couple of weeks to a couple of months, the land is actually the most important part. And that's because it provides some sort of memory to the system. So the land surface states, like soil moisture, evolve slower than the atmosphere. So it provides us forecast skills at these sorts of timescales. And this is, for example, quite relevant in Australia at the moment for seasonal prediction of droughts, trying to forecast when they might start and end. The land is also really important because it interacts with the atmosphere. So it's not just some slab that sits under it, but it influences what happens in the atmosphere. So this picture here is from Western Australia, and there's a rabbit fence running through this landscape. So there's a really sharp transition in the land cover type. With this side you have native woodland, and this side it has been converted to agriculture. And if you look at this picture, you can see the atmosphere looks quite different above the two land use types. So the land influences things like the rainfall through evaporation and temperature and so forth. I'll show a bit more on that later. And it also alters the boundary layer, which is the bottom layer of the atmosphere that is influenced by the land, and the depth of that varies by day and by the state of the atmosphere and the land, and diurnally. So since we're in the COE of climate extremes, relevant to that is also how the land influences extremes of climate, both by amplifying and dampening some extremes, such as heat waves. I'll again show more on that later. And also many of the impacts of these extremes are felt through the land, such as droughts. So we all probably agree droughts tend to start with some lack of rainfall. But if there's ample water on the land, then that rainfall doesn't necessarily cause big impacts. It's really when the rivers start running dry or the soil moisture is depleted, so the plants start suffering. So the land is important for that. Also, for example, for flooding, it's really how the land behaves once that heavy rainfall falls on it. If it absorbs the water or if it starts running out and flooding our landscapes. Now, land surface models themselves are used across a variety of scales in their applications. So we run them in so-called offline state, where we give it the observed meteorology and run them back in time. And we do that at the smallest point scales, which could be about a square kilometre, where we have observations relevant to land, all the way to the CREDIT global observations normally at 0.5 degree resolution or so. And these scales are, for example, used to construct that global carbon budget that I showed you and estimating the land sink size. And we also use these offline runs to evaluate the models against past observations and also for all sorts of process scale understanding. And then, of course, we run the land models inside the coupled climate models, where they feed into the future projections of climate. And in terms of the scales that the land surface models represent, they start from the very small scales of leaf stomata, which are much smaller than a millimetre. And actually, a lot of the core functions inside the models work at that kind of scale. And then the purpose of the models is to scale up those leaf scale processes all the way up to whole leaves, ecosystems, and finally to the whole globe. Now, inside the land surface models, they represent 3 key cycles. So that's the energy cycle, the water cycle, and the carbon cycle. And I will go through the main process for each of these cycles in this talk, and how they're modelled inside the land surface models. So each land surface model is the sum of those different parts. But whilst I go through those, do keep in mind that many of these processes are closely interlinked and interact in various ways. For example, variables like evapotranspiration actually relates to all 3 of the cycles, Yeah, so a real model probably looks something more like this rather than these nice schematics over here. Okay, so I'll start with the energy cycle. So this figure just shows the different energy fluxes going in and out of the atmosphere and the land surface. So on this side, you have the short wave, so the radiation coming from the sun. This side is the long wave, so that's the infrared radiation emitted by the Earth and then captured by the atmosphere. And you'll see the short wave that's coming in and out very strongly. That's both diurnally, seasonally, and by latitude. Long wave less varies so, and the two terms are more or less balanced. So the land is important for determining how much of that incoming solar is bounced back into the space. And the land is also important for determining what happens to that energy that stays on the Earth's surface, that's not bounced back to space. And so the land converts that to two main fluxes. So one of them is latent heat, which is the same thing as evapotranspiration, so that's a water flux. The other one is sensible heat, which is a heat flux. And even though these two terms are quite small, 24, 78 compared to hundreds for the other ones, they actually are quite important for the land process as well as the atmosphere. So this is the basic energy balance equation, which determines the net radiation, which is the key variable. So that's the available energy that's left on the surface, which is the sum of the short wave and long wave that comes in and goes back out. And this equation assumes that the land as a thin layer doesn't store any heat over long timescales. Now we can slightly modify this equation where we can express the outgoing, so the reflected solar radiation, as a function of the albedo, which is how reflective the land surface is. And this is actually really important for determining how much of that solar radiation stays on land as energy and heated. And this varies massively across different land types. So if you look at the forest over here, it has an albedo of maybe 15%, meaning only 15% of the solar radiation is reflected back into space. The rest stays on the land surface. Crops are a bit more reflective, as are grasses, maybe around 20%. Deserts, again so. And snow and ice reflect, in some cases, most of the radiation. And one example where this is really important is the Arctic amplification of temperatures that you've probably heard of. So in the Arctic has warmed a lot more than the rest of the Earth's surface. And that's a lot of that is driven by the albedo changes, partly, of course, due to the disappearance of the sea ice, but also the fact that where the land used to be covered by snow seasonally, now perhaps looks more like the forest over there, leading to a positive feedback loop, amplifying the temperatures. For example, in Finland, where I'm from, Decembers are now 5 degrees hotter than they used to be, so it's a massive warning that has occurred. Now we can also express this equation slightly differently. So this is again the net radiation, which is the balance of the shortwave and longwave fluxes. And as I said, the land determines... There's some stuff missing from the slide. Okay. So the land determines what actually happens to these energies. So as I said, it converts it to latent and sensible. And there's also a term which is the ground heat flux, which is important at the diurnal scales, so night and day, for example, but over scales from weeks to months to years, what comes in and out is more or less zero. So we tend to ignore that part. What's doing this? Okay, so the reason the land is important is when there's ample water available, like in a landscape that might look like this. A lot of this net radiation is turned into latent heat. And that leads to a moist atmosphere. It also provides evaporative cooling, as that energy is not available to turn into heat. And it tends to lead to a shallow boundary layer. In environments that look more like this, most of that net radiation goes to sensible heat that heats up the atmosphere just because there is no water available to evaporate. And this has feedbacks to the atmosphere. So normally we have some kind of drying of the landscape. You start off wet, and it dries out, say, during the summer when it gets hotter and the rain might stop. And these change the fluxes going into the atmosphere. And this leads to a number of positive feedback loops. So as you're no longer evaporating, you're not putting moisture into the air, so that has an impact on your rainfall. And that leads to further drying of the landscape when you no longer get rainfall. The increased sensible heat also leads to higher temperatures, which can again dry out the landscape and leading to more sensible heat being pumped into the air. And over time, this just shows how this might lead to an accumulation of heat in the atmosphere and an increasing height of the boundary layer. Now, where these sorts of feedbacks are important tend to be the regions that are not the wettest or the driest, and the location of them vary by season. So if you, for example, think of a Mediterranean type climate, they tend to get lots of rain in the winter, whereas in the summer that rain stops and the landscape starts drying. So that's one classic example of where these feedbacks are important. This figure shows where the models suggest these regions are during the Northern Hemispheric summer, which tend to be those transitional regions, but there is actually quite a lot of uncertainty on where and when the land plays a big role in terms of the feedbacks into the atmosphere. And one example of an event that there's now lots of evidence for that the land played a big part in amplifying is the big heat wave in Europe in 2003 that led to something like 30,000 deaths across Europe and hugely hot conditions. And there's now good evidence that that event was amplified by the fact that the land dried out and provided a feedback to the atmosphere, increasing the temperatures. Now, in my work, I've looked at how well the models actually do this partitioning of the net radiation. So this just shows a simulation from one point, just a short time series, and the black is the observations. And somewhere in the middle of this time series, you have a dry period where you get that transitional drying in the land. And as you can see here in the latent heat, these coloured lines, which are different models, are pretty different from each other and also from the observations. So they tend to start drying out too quickly, pumping out all this sensible heat into the atmosphere. So that's one important process where the land surface models need improving and are not doing this necessarily well at the moment. Okay, so that's the energy cycle. Next, I'll talk about the water cycle. So you've probably all seen this kind of figure on the global hydrological cycle. There's many processes on the land that happened, and the models themselves include obviously very simplified representations of many of these processes. And not all models consider all the processes that we know to occur on the land surface. So these processes are, of course, how the water flows over the land and into the oceans, and how much is lost through evaporation and what enters the soils. Now, the basic premise of the water cycle is the water balance equation. So a bit like energy, the models have to conserve the water. And the equation states that the precipitation, that's the input coming in, must equal what's going out. So the big terms are the evapotranspiration and the runoff. And then we have the change in the storage, so change in the soil moisture. And the key role of the land surface is to determine how this rainfall falling over the land is partitioned into those different processes. So globally, out of these, evapotranspiration is by far the biggest flux. It's maybe about 65% of the rain that falls on land is turned into evapotranspiration. But of course, this varies spatially quite a lot. And this is also one point where the energy and water balances are tightly coupled through the evapotranspiration. And over short timescales, a bit like with the ground heat flux, the change in the storage can be important. But over long timescales, from years to decades, the change in the storage is normally negligible unless there are strong trends in, say, rainfall in a particular region. In terms of modelling these fluxes, they're actually the sum of many different processes. So evapotranspiration consists of transpiration from the plants, as well as interception evaporation. So that's the water, the rain that falls on the leaves and evaporates straight away before reaching the ground. That's quite a small part, but can be important somewhere like the Amazon. Then there's soil evaporation, straight from the soil, and also sublimation, which is when ice or snow turns directly into evaporation. That's also quite a small flux. And globally, out of these terms, transpiration is the most important. There's uncertainty on the exact numbers, but perhaps up to 80% of the evapotranspiration comes from the plants. But of course, this doesn't hold in places like the desert, where there's no plants. In terms of runoff, there's two main terms. So one is the surface runoff, so say the water we see in the rivers, and also base flow, or also called subsurface runoff, which is the water flowing inside the soils. And in most wet environments, a lot of the rainfall actually is turned into runoff. And the storage part is more complex, and it depends on the other terms, but it depends on how much water is infiltrated into the soil, and then how much is lost to evapotranspiration and subsurface runoff. Now, in terms of surface runoff generation, the models consider one or two main processes. Not all of them have both. But the first one by which surface runoff is generated is infiltration excess. So when the water can't infiltrate into the soil quick enough to be absorbed, but starts running over the land. The other process is saturation excess, when the soil profile is already full of water, so it can't absorb anymore. For example, the Australian land surface model, up until recently, only did saturation excess, which in Australia practically never happens, so you never get any runoff, which is not very realistic. Evapotranspiration, it's normally modelled using some form of the Penman-Monteith equation. I won't go into the details of this, but it's basically a function of the atmospheric state. So that's the radiation coming in, that's the energy required to evaporate the water. Wind, so if you imagine a really windy day, your washing is probably going to dry a lot better because that enhances the evaporation. And also humidity. So a lot of you were in Darwin recently. I would imagine it was very hot and moist. So your washing is probably not going to dry there as well as it would somewhere like Alice Springs if it's equally hot. And of course temperature comes into that as well. But what the studies show, that temperature is not actually the most important thing. So what a lot of you have probably heard, that in a hotter world it's going to evaporate more and we're going to get drying. But actually many studies show that radiation and wind speed are much more important in determining how much is evaporated from the land. And then we have one more term, which is of course the vegetation control via transpiration. Now, can anyone guess what is the one more missing ingredient that we need in this equation? Sorry? Yes, pretty much. We need some water. So, of course, for evaporation to happen, we need some water. So that also comes into this equation. So this, if you wish, this represents some potential rate of evapotranspiration if we had unlimited water in the landscape. And the models then reduce this depending on the soil moisture using really simple equations that currently are not really based on any proper observations. So this is actually one key process that, for example, some of us in the centre are working on. So how does the water limitation impact this equation? And then in terms of soil moisture, that includes a number of different processes. But in the models, in practice, you have some number of layers that the soil is represented as. And some models also consider a groundwater aquifer that can recharge the soil moisture and store water. That's currently done in the latest version of the Australian land surface model, for example, but not considered in many of the CMIP 5 models. And the way the models treat the soil moisture, they normally just consider the flow of the water up and down the soil column. So they don't normally simulate how the water will flow across horizontally from one grid cell to another. And one important part of this is, of course, the soil properties that we need to consider in the model. So you can probably imagine that water will flow very differently through a very clay soil versus a very sandy soil. And the two key laws or equations that the models use to simulate the soil moisture movement is the Darcy's law, which determines the rate of the water movement. Another one is the Richards equation, which determines the soil moisture content in each of those layers. And then, of course, the models need to consider snow and ice, not something we perhaps think about in Australia too much. But if we look at globally, it's of course massively important in many parts of the Northern Hemisphere. And the models consider a number of processes. So for ice, they can allow the soil profile to freeze, and this will of course affect the hydraulic conductivity, so how well the water can move through the soil. It will also limit the fluxes, so plants, for example, won't be able to take up water from the soil anymore for transpiration if it's frozen. And in the models, we often represent some fraction of the grid cell can be frozen and the other one can be melted, so they can coexist. In terms of soil, a bit like the soil, there's normally some number of layers that it's represented as on top of the soil. Again, it can be just some fraction of the grid cell. And the models will consider, of course, how much snow it will accumulate based on the rainfall. Also, how it will melt and refreeze depending on the temperature. Sublimation, which was snow or ice turning into evaporation. And then how the snow will compact over time and how that might affect the flow of the water through it. So that's the basics of the water cycle. And then the one last thing that the models consider is, of course, the carbon cycle, which I showed is important, for example, from the long-term predictions. So in the models, they consider two very big fluxes. There's some numbers over there in petagrams per carbon, whatever that number means, a very big number. So one of the terms is the photosynthesis, so that's the carbon taken up by the land biosphere. And then the other part is the respiration, so a bit like we breathe out CO2, so do the plants and the soils. And those two big terms, the respiration from the soil and the plants, roughly equal what's taken up by the plants through photosynthesis. Currently, photosynthesis is ever so slightly bigger, meaning the land as a net is taking up a bit more carbon than it's putting out into the atmosphere. And whether it's a sink or source is a small balance of the two numbers. So it's important to get them right in the models. And this was just to point out that the land actually stores a lot of carbon. So the atmosphere holds about 750. Together, the plants and the soils hold over 2,000 petagrams of carbon. And the soils in particular hold a lot of carbon, and it's the fate of that carbon that's also important for determining the future carbon sink. And I thought I would just point out that we don't yet consider cows in the models. So the two main terms are the photosynthesis and respiration. So as I said, respiration is comes from the microbes in the soil through processes like decay, for example, and also maintenance respiration by the plants. So for their functioning, a bit like us breathing out the CO2. And another part that's important in the carbon cycle is the nutrients. So those are essentials for the plant photosynthesis and actually using up that carbon to grow. And an increasing number of models now consider this, and they explicitly stimulate how those nutrients also flow through the ecosystem, as well as the carbon. I think quite a few of CMIP6 models will be doing that, but I think it was perhaps only 2 CMIP5 models that considered these processes. The models also need to consider what happens to that carbon that the plants photosynthesize. So they need to have some rules and dynamics over where that carbon goes, whether the plants will put it into leaves, whether they will store it in the wood, or whether they perhaps put it into roots. And those will also depend on the environmental conditions. You could, for example, imagine a really dry environment. The plants might want to put more into the roots to access more water. But that's still really uncertain in the models, and we don't really know how to best do that. And then the models also need to consider a number of disturbances that will affect the amount of carbon in the landscape. So these could be things like fire, which is really important in Australia, or land use where we change that vegetation type. Now in terms of modelling photosynthesis, so we need water, CO2 and light for photosynthesis, as well as enzymes which actually drive that reaction. So in the models, so on this axis you have photosynthesis, and here it's increasing CO2. So in the models, the photosynthesis is the minimum of 2 main limitations, which are represented by these curves. So the orange one is the enzyme limitation, how much enzymes there are, how active they are to drive that process of photosynthesis. The other one is light limitation and how efficiently the plants are using that light. And it's the minimum of those 2 curves that the model actually considers as photosynthesis. Now, currently we sit somewhere here, if you can see the shading on this line. So this value is the leaf internal CO2. So it's a little bit lower than what's in the atmosphere, but the two are closely related. So as we start increasing CO2, can any of you guess what might happen to the photosynthesis in the models and in real life? Decrease? Yes, up to a point. So we currently sit somewhere here. So as we increase the CO2, the land is still photosynthesizing and taking up more of the carbon. But as we start entering somewhere here, it will start following this green curve. Up to some point, it will increase, but then this relationship will flatline. And that's quite well established from lots of different plant experiments. And this will mean that at some higher CO2, which will depend on the plants and many, the land will no longer take up that 25% of the carbon. But there's high uncertainty exactly where this will happen because the shapes of these curves will depend on the vegetation type, for example. So it might not be the 25% anymore, and in fact there's a number of plants already, so-called C4 plants, that already sit somewhere on this flat part of the curve. And C4 plants are mainly grasses that live in hot, dry conditions like much of Australia. Now, it's at this smaller scale in the model that the carbon and water cycles are intrinsically linked. So these are the plant stomata. So they open up to take up CO2 from the atmosphere, but as they do that, they lose water through transpiration. And this sits at the heart of all modern land surface models. They consider this process. So while I showed that photosynthesis will increase up to some point, stomatal conductance, so the water loss through transpiration, actually increases probably already at current CO2 levels. And this is also well established from plant experiments. So this means, so that happens because the plants can close those stomata more while still maintaining a similar influx of CO2 just because the atmosphere now holds more of it. So this means that the plants can actually use less water to still photosynthesize the same amount at the very smallest scale of the leaves. But what this means for the water cycle can actually be quite complicated. So at the leaf level, they're using less water. But what we are seeing from the satellites is that, for example, much of Australia is greening up. So here I'm showing the trend in the satellite greenness. And that's because the plants now at the higher CO2, they can photosynthesize more, so they can perhaps grow more leaves. And what this means for the water cycle is that they might be losing less water at the leaf scale, but if they now have more leaves, overall they are transpiring more. And this seems to be what we are seeing over Australia in not the wettest or the driest part, but the sort of subhumid environments. So where these green bars are, we are seeing vegetation greening due to the CO2. And this is leading to an increased evapotranspiration at the ecosystem scale. And this has implications for runoff. So if you remember that water balance equation, if we have more evapotranspiration, we get a reduction in the runoff, which of course has lots of implications for the water resources for humans. How these different processes play out is actually a big uncertainty in the models. In terms of the water cycle implications. Now, at the heart of the carbon cycle modelling is, of course, how the models represent the vegetation. And this is perhaps where land surface models diverge the most. At the heart of this is the plant functional types. So that's how the models represent different vegetation types. And these are just very broad classes of vegetation, like broadleaf, evergreen or deciduous trees, shrubs, grasses, perhaps crops. And in any given grid cell, either the model will just assign it one plant type, or in the climate models, we often have some fraction of different plant types. But they don't normally talk to each other. They just exist as separate entities in the model. Another key property of the vegetation is, of course, the amount of leaf area that the vegetation holds. And that will determine things like the amount of transpiration. The leaves will also provide shading, so that then has feedbacks for the soil evaporation, for example. And in the models, some of them simply use satellite observations to work this out. So they might calculate some long-term average leaf area for a given pixel. That will vary seasonally, but it will not vary from year to year. So rain or shine, that model will have the same leaf area every January, February, and so forth. And for CMIP 5 models, approximately half of these were doing this. And in terms of CMIP 6, I know for the Access model, and one version of Access will be doing this, and one version is actually stimulating how the leaf area changes according to the environmental conditions in the model. And then there's, of course, vegetation structure, which, for example, has impacts on the atmosphere through the roughness of the land surface, for example. And this is where the models have quite varying complexity. So some of them use the so-called big leaf vegetation, where they treat the system as it was one big leaf, so they work out the basic fluxes for that and then scale it up using the leaf area. And now the most state-of-the-art models consider demographic vegetation. So instead of the vegetation sitting in those separate boxes, they will actually coexist. They can compete for resources and they can interact. And in the most advanced models, the vegetation type can actually change with climate change and so forth. Now to finish up with, I just wanted to mention some challenges that are perhaps unique to land surface modelling, as well as a few topics of cutting-edge research in land surface modelling. So where the land is very much different from the atmospheric or ocean modelling is that those two need to simulate the movement of air and water, which is still very difficult, otherwise we would have it exactly correct. But there's still one sort of medium that they need to consider. Because if you think of the land surface, it varies hugely from one area to another. So this just shows some very broad vegetation types across the globe. And in the models, these are currently those plant functional types. But for example, what in the models we might call broadleaf evergreen vegetation, in real life could be something like the eucalypt forest in Australia. It can be something like the Amazon rainforest. And I don't think anyone thinks those two will be behaving in the same ways. But it's very hard to try and find common relationships and really simplified representations of the thousands and thousands of plant types that can coexist even in a tiny area of forest. And the model can normally assign all of that just one value. And that's before we even start to consider the whole continuum of ecosystems that are on land. And of course, one more challenge comes from what's underground. So we need to know what the soil properties are like to get the water movement right, or how the vegetation react. We do have lots of soil maps for the Earth where we can work out perhaps where it's sandy, where it's clay, and so forth. But in reality, there's huge uncertainty as to the actual soil properties at any given location. There's, for example, a recent soil map that I've seen for Australia where you can clearly see the state borders in the map. I doubt the soil type changes as you cross the state border. And also, we don't necessarily know where the groundwater exists underground. It's very hard to measure from anything. Yeah, it can be really important for example, many ecosystems in Australia. Then I also mentioned the models vary massively in terms of their vegetation. So this is a huge area of research, not just in the core land surface modelling, but the broader ecosystem modelling research area. So one is introducing some competition between the plants in the models. And the other one is actually having dynamic vegetation, which is, for example, important as we move into the future and the climate is changing. I don't think we think that the vegetation will stay exactly as it is. But this is quite challenging to do in the climate models, even for the present conditions, because to be able to predict the vegetation type more or less correctly from the climate, you first need the climate to be right. And of course, there can be fairly big biases in the climate models. Another one is disturbance, which I already mentioned. So maybe you're surprised to hear that, for example, the Australian land surface model doesn't actually consider fire at all. It is being added currently, but there's many processes that are missing. And also land use is not necessarily considered in appropriate ways. For example, in the CIMMYT 5 models, we might be changing the land cover type through some prescriptions, and some of it comes through the scenarios. But I'll show you what we are missing in the next slide. And also, what most models don't let the vegetation do is to wilt and die. That's the massive research area, actually, including some people in the centre. But it's really challenging because we don't necessarily know when a certain plant type is going to succumb to drought, and how we can actually simplify this in the models. And then there's also a push to move away from these fixed PFTs and to consider more broad spectrum of plant traits to represent the vegetation. So the plant traits could be things like the leaf area or how efficiently they use water and so forth. And then one more big research area is actually adding human influences into the models. So one example is, for example, irrigation, which is really important in places like the Murray-Darling. We take out lots of water from the river systems, so that reduces runoff. But that also adds water into the landscape, so perhaps we are increasing the evapotranspiration that way, and that can have influences on the atmosphere. There's a big global push to work on this in land surface models at the moment, but most models don't yet consider this. Also, land use is not simply about changing a forest to crops, for example. We also have things like secondary forests, which changes the age of the forest, which then changes how it behaves, how much carbon it's taking up, or how much water it's using up. And one more thing that we are generally missing in the models that Melissa works on is adding the urban environments into the models. So even though they're fairly small land areas, they can have big impacts globally. And of course, since most of the human population lives in urban environments, it's important to add those processes in the land surface models. So just to quickly wrap up, I hope I've convinced you the land is important at multiple timescales, from the short weekly timescales all the way up to the decadal or centennial long-term projections. And the land surface consists of 3 main cycles, so the energy, water and carbon, which all interact. And the land surface provides important feedbacks to the atmosphere in the climate system, so that's through changes in the precipitation and temperature, for example. And the land is also important for many extremes, like droughts and heat waves. Either can dampen or amplify those. or we feel a lot of the impacts through the land. And it's a very important carbon sink, which will have implications for future climate change. And just before I quickly wrap up, 2 suggested readings for anyone who might be interested. There's a nice new textbook by Gordon Bonan, who's a big professor in this area in the US. There's also a nice review paper by Andy Pittman, which goes through some of the evolution and the basic process in land surface models. I will point out it's from 2003, so it's not exactly cutting edge, but might be worth a read. Oh, thank you.